Welcome again to the video lecture series for GG and OCN312, the topic of the class being Advanced Mathematics for Engineers and Scientists. Now we're going to get into Chapter 2, the topic of Chapter 2 being first order differential equations, and this is Chapter 2 of Greenberg's text. And this video will be about the very first part of the text, and that's addressing the linear homogeneous first order differential equation. To summarize what I'll talk about, first I'll define a linear first order uh, ordinary differential equation, and then we'll talk more specifically about how to solve the homogeneous case. What I'd like you to take away with this is the knowledge of how to recognize a linear first order ODE and then how to solve the homogeneous case. So the general linear first order ODE, ordinary differential equation, may be expressed as a coefficient that depends on x times y prime, the first derivative of y, plus another coefficient a sub 1, which could also be a function of x times y itself, again being a function of x, is equal to a term that's independent of y. So again, this is a ordinary differential equation because there are only derivatives with respect to one variable, that's x, and it's first order because the highest derivative is 1. Now, if a0 is non-zero over the interval of interest, we can of course rewrite this equation in terms of with the first derivative by itself as a1 of x over a0 of x, y of x equals f of x over a0 of x, or in a more succinct form, just y prime plus p of x, the coefficient on the function of y itself, and the right-hand side, again being the part of the equation that is independent of y, is just written as q. So solving equations of this form is the topic of Chapter 2. That is, if we know p of x and q of y, we're given the functions p of x and q of y, we pose the question, what is y of x? And it's and y of x is the function of y that satisfies this linear first order equation. Now, the rest of this video, I would like to talk about how to solve the homogeneous case. And the homogeneous case is the case in which the function on the right-hand side, again being the part of the equation that's independent of y, that term is equal to 0. So the general homogeneous first order linear ODE is y prime of x plus p of x times y is equal to 0. And so this is the focus of solving this is the focus of the rest of this video. So let me rewrite this equation so we can see it at the top of this new page here. So we have y prime plus p of x times y is equal to 0. And it turns out that this equation is separable. Meaning we can separate all functions of y on one side of the equation and all functions of x on the other side. And separable equations have a relatively simple solution. So we have dy dx is the first term is equal to p of x times y. And if we divide both sides by y, we have 1 over y dy and then dy and then p of x dx. So I've divided both sides by y and I multiplied both sides by dx. And this gives a separable form. So we can, because it's separable, we can solve this by integration. We can integrate the left side with respect to y and the right side with respect to x, and we get the log of y is equal to the integral of p of x dx, and there plus our integration constant, and that gives us the solution that y is equal to e to the minus p of x dx plus c, and where's the minus sign here? Oh, I'm realizing I brought the p times y to the right hand side of the equation, so I need to have a minus right here because I just brought it to the right hand side of the equation, so I need the minus there and the minus there, and that gives the minus there. And with this solution, we see that we have e to the c times e to the minus p of x dx, because the exponent of a sum turns into a product, and e raised to a constant power is just another constant. So we can write that as y is equal to a e to the minus the integral of p of x dx. Again, p was the function that was multiplied by x in the original equation. Another detail I'm noticing I'm sort of glossing over here, but let me fix this. So we know that the absolute value of the log of the absolute value of y is equal to this, and therefore the absolute value of y is equal to e to the raised to this exponent. And so with that in mind, y can be positive and negative, so therefore a can be positive or negative, i.e. a is equal to positive or negative e raised to this first constant. Okay, so y can be positive or negative and still solve this ODE. And this is the general solution for the homogeneous case. Now, to find the specific solution for a given initial condition, then we would have to solve for A. So in other words, A is determined from a specified initial condition. And remember, an initial condition is a condition on Y, or it's on Y specified at a single point in X. And if that is specified, then we can solve for the specific value of A for that specific initial condition. So here's an example. So let's say we have Y prime plus 2X, right? And that's P of X times Y is equal to 0. Again, we can write this in separable form with functions of Y on the left and X on the right hand side. So the intermediate step is moving the function of X to the right hand side. So we get minus 2X times Y, and therefore we have dy over Y is equal to minus 2X dx. And if we integrate that equation, we get the log of Y, the log of the absolute value of Y is equal to the integral of minus 2x is just minus x squared plus a constant. And therefore we get Y is equal to a e to the minus x squared. Okay, and again, A can be positive or negative because associated with this constant, e raised to the c power can be positive or negative to solve this equation. Okay, that's our general solution. Now, suppose we're given an initial condition. And again, initial condition, the word initial comes from the case in which typically the value of Y is specified at the very beginning, or at X is equal to 0. But this word initial is applicable. Well, initial condition is really applicable for any value of X. So suppose our initial condition is Y where X is equal to 0, or sorry, Y where X is equal to 2 is equal to 5. That is, if Y evaluated at point A is equal to B, where A is equal to 2 and B is equal to 5. So if we want to find the solution for the case in which at point X is equal to 2, Y is equal to 5, then all we have to do is substitute 2 in for X, 5 in for Y, and solve. Just solve for A. So just substitute A, which is 2, for X, and B, which is 5, for Y, and solve for A to get our particular solution. So here we have 5, Y is equal to 5, and we have A e to the minus Y is equal to 5 when X is equal to 2. 2 squared is 4, and therefore A is equal to 5 e to the fourth. And our particular solution is y is equal to 5 e to the fourth times e to the minus x squared, right? And that can also be written as 5 e to the minus x squared minus 4. And this is our final solution. So that is an overview of how to solve the homogeneous case, that is the case in which the right-hand side is equal to 0. I showed you how to solve it generally for any value of p to get this solution, and then we looked through this example. Okay, so the next sets of videos will address cases in which the right-hand side is not equal to 0, or the non-homogeneous cases.